Hello, Chem 115 students. Here we have another mini lecture from topics from chapter 2. Some things we didn't quite thoroughly discuss in class today. I hope you're reading the book. I hope you finished the activity 10B that we were working on in class today. Here's some things to help you. The point of all of this is to understand how electrons are arranged in atoms, and they're not always moving. They're restricted to certain places where they're going to be occurring, where they're found based on how much energy the electrons have. And so the energy of the electrons gives them certain areas where they will occur that we describe as being quantized. They can only be in those certain locations, nowhere in between. It's just like you're either going to be on the first step, the second step, the third step, the fourth step, and never a half step in between. Electrons aren't either. And so we describe the electrons as being in energy levels that you have seen described today. And the nucleus with its protons and neutrons is going to be considered the middle. Building outward from there, as we saw in the shell models today, are the various shells. And the first shell is the one that's closest to the nucleus. The second one is farther out. And you keep on going, adding shells out from the nucleus at different energy levels. The closer they are to the nucleus, the lower energy, because it's low energy for a negatively charged electron to be close to that positively charged nucleus. So we think of these shells of electrons where these will be found, and we will describe them according to different other descriptions here we'll see. They're found in regions that we call orbitals, regions that are within the subshells of the electron configuration. There are two shapes of orbitals. There's either an s orbital, which you can think of as being like a sphere, and the p orbital, which is kind of an odd shape, sort of like a pinched balloon. It depends on which picture you look at. And there's three different p orbitals going in different directions, as though they would be the x, the y, and the z-axis orientations for those three p orbitals within the subshells for a particular shell. They will be described with S, P, D, or F. The D and F ones we will not describe in more detail. These are also considered to be like clouds of electrons, where the electrons are moving about in fast motion. So these s orbitals, being spherical, have one for every shell, shell 1, shell 2, shell 3, shell 4, with a maximum of 2 electrons. But that is because every orbital has at most 2 electrons. And so an s orbital, there's only one of them ever in a shell, and it will always have only 2 electrons. The p orbitals then are going to be in sets of 3 equivalent orbitals. If they each have 2, that gives you a total of 6 electrons maximum for the p orbitals. The d orbitals come in sets of 5, and the 5 orbitals are equivalent in energy. With 2 each, that gives you a maximum of 10 electrons. And we have shapes that are complex and not worth our further conversation now. Then there's f orbitals, which we will not describe at all, and I can't even tell you where I've seen them. They're very complex, and there's 7 equivalent orbitals. Well, if there's 7 orbitals, 2 electrons per shell, that gives you a total of 14 electrons possible for f orbitals. So one of the things you need to look at are these charts from your textbook and from the POGIL activity today. For every shell, there are subshells. Within subshells, there are orbitals and a different number of electrons for each. So the first shell has one type of subshell. The second shell has 2 subshells. The third shell has 3 subshells. The fourth shell has 4. Every time you have an s orbital or an s subshell, I know these are tricky terms to say straight, there's only one of them. And every time there's a p orbital, there's always 3 of them. So there's 1 and 3 in the third shell, 1 and 3 in the fourth shell. And every time there's a d orbital, there's going to be 5. Every time there's a d subshell, there will be 5 orbitals, whether it's in the third shell or the fourth shell. And that unique one for the fourth shell then becomes this F orbitals in the F subshell. So each of those numbers of electrons corresponds to 2 per orbital. Total electron capacity for each shell then depends on the number of subshells. If you add together the numbers of electrons from each of the orbitals for each shell, you get 2, 8, 18, and 32. Different representations of ways of seeing these things. Now, how do we use this? Or how do we work with it? Each of these shells and subshells has energies associated with them. The shell closest to the nucleus is the shell number 1, and they get to be higher energy as they go away from the nucleus with higher numbers of shells. The first subshell is only within the first shell, and it's only one type. It sounds like silly to call it a subshell when it's only one, but that's how it's described. The second shell has 2, with the 2s, the s subshell within the second shell being lower in energy than the 2p, the p orbitals within the second subshell. The third subshell is where things start to get crazy, because all of a sudden you've got 3 types of subshells, but they overlap with the subshells from the fourth shell. And that makes for some confusion, which is why we'll limit how far we're going to be able to describe electrons in these things. So you'll need to be familiar with the notations that these subshells have. The number in front tells you the shell. The letter following describes the subshell type that occurs within that shell, and which electrons are there is what you'll see. These are all related to the colors of flames as we were describing in class on Tuesday. The colors you observe in flame have everything to do with electrons, how they get excited from lower level energy to higher level energy and then relax down to their normal energies, giving off light of characteristic colors. So what we need to be able to do is use these subshells and such to be able to describe electron configurations. When we think about this, we describe the periodic table in terms of blocks. Describing the periodic table in terms of blocks, exactly where we left off in class today on Tuesday. The S block of the periodic table is the first 2 columns on the left, which is for the elements whose last electrons are going to go into S subshells. Which S subshell depends upon which shell the outermost electrons are in. The shell number is equal to the row number, as we were beginning to describe, or sort of described in class. So the shell number equals the row number, and you'll have to look for that as you think about these things. So the row number gives you exactly what shell those electrons are in when you're looking at a particular element for the last electrons. And so the S block is on the left, the P block is on the right, and the D block is in the middle, and we won't look at electrons there or elements that land there as much because they're more confusing, and that would be the transition elements. The F block is the intertransition elements. Notice that the number of columns across each block corresponds to the number of electrons in those types of subshells. There's always only 2 electrons in S subshells. There's always a possible number of 6 electrons in P subshells, and there's always 10 in D subshells and 14 for F. So that corresponds to the width of each block. Using this, you can come up with an electron configuration for an element if you know where it sits in the periodic table just by following across the rows and columns. So aluminum would be right here. If you're trying to determine its configuration, you just start from the beginning over on the left. Where else would you start? Element number 1, and each element has 1 more electron than the previous one, so you just think in terms of reading across the periodic table until you reach the number of the element that you wish to describe. So for aluminum, let's do aluminum first. So we'll write it up here. We'll be starting with 1s, and by the time you finish that first row, you'll have 2. When the S subshell is full, there will be 2. After that, you go to the 2s subshell, and it will also be filled. So 2s, 2, remembering the superscripts describe the number of electrons in each shell. After 2s, we go to 2p, and when it's filled, which it needs to be to get beyond the electron, get up enough electrons to get up to the number for aluminum, which has 13. Then we'll have to have all 6 of those p electrons. After 2p comes 3s, which of course needs to be filled before we're going to get up to aluminum. And so 3s, s2 will be filled. Following that becomes one more electron must be in the 3p subshell, and so only one more electron is needed. If you add up all the superscripts, that gives you a total of 13 electrons as required for aluminum. Now, if we will go on from there to do the configuration of phosphorus, you have to figure out where it is in your periodic table. So you look in your textbook and you realize that there's another square here for silicon, and then after that comes phosphorus. Well, I didn't make my squares very big, and a few more, so there's a total of 6 elements across that row, and so phosphorus would be not too much different. Okay, so phosphorus will have almost all the same electrons as aluminum, so we'll begin in the same fashion. We'll have a couple more, so we'll start with 1s2, and it'll continue with 2s2. They always fill the lowest energy levels first, and so they always begin in the same patterns. 2p6 will be the next electrons. If you count up to there, you'll see that would be 10 electrons. Oh, my tool's not writing well today. That right there is equivalent to the electrons for the noble gas neon, which we'll talk about more later. And past that, we have the 3s2, and 3s2 is followed by some p electrons. Well, this time phosphorus is the 3rd column over in the p block over there in the 3p, so we'll put 3p and a total of 3 electrons for that one, for that subshell. So far, so good. Okay. This slide shows you that the textbook actually shows every electron configuration for the first 20 elements. These are the ones that you should be familiar with and be able to identify as when they're represented correctly. Once you understand the patterns from the S and the P blocks, it should be fine. Not so bad once you see the patterns and realize that you end up with the last ones in 4s2 for calcium. After that, it would become interesting with d electrons, and we won't be responsible for understanding how to do those in this course. If you want to think about how the elements are similar by the periodic table, we look at their valence shell electron configurations. This would be at the end of the activity that we didn't quite get to on Tuesday, but we were getting very close to making those realizations. Some of you may have seen it. For the elements that are in group 1A, the alkali metals, they all end in a configuration with 1 electron in an S subshell. For group 2, they all have 2 electrons in an S subshell. The shell, depending upon which row of the periodic table they are found in. The group 7A electrons, the halogens, are going to always end up with 7 valence electrons. The outer shell will be a total of 7 because the valence number equals the group number. And so you can quite easily connect those ideas when you're paying attention to it. Number of valence electrons is exactly the same as the group number, as long as we're sticking to the main group elements, which is all we need to do for our course. Okay, so these will have 7 valence electrons ending with P5. And you have to recall that the 2 S electrons that precede them in every case are part of the same shell, as indicated by that first number being the same in front of the S and the P. The last set is the noble gases, and they have something in common. They don't all have P6, most of them do, but these are all going to be full outer shells. The valence shells are always full. And so that's characteristic of the noble gases, and then one of the important things that we'll want to keep track of as we move forward into the next chapter's discussion. The difference with helium from the others is that helium can't possibly have p electrons, or not even close to 6 p electrons, because helium has a total of 2 anyway. but the electron outer shell, the valence shell, is full. One thing that an extension of this valence shell concept is to use electron dot symbols. These are rather simple and not confusing to most people, but it's a way of representing the valence shell, valence electrons for these various elements. And so the valence electrons are represented using dots around the symbol of the element, and for every group they have the same pattern. For group 1, 1A, the alkali metals, they all have a single dot. Group 2 has 2 dots to represent their 2 valence electrons. Group 3A, boron, aluminum, gallium, will have 3 dots for their 3 valence electrons, and so on, all the way up to the full set of 8 dots around the element symbol for the noble gases. For these are all called a full octet. For the elements in the noble gases after neon, helium can't have that many electrons. So the electron dot numbers correspond to the valence electrons. Not hard to do. All right, a few more comments. The arrangement of the atoms, electrons in shells and subshells will go as follows. The electrons will always be in the lowest energy orbitals possible, always beginning with 1s. One electron is going to go into each subshell, each orbital of the subshell before a second one goes in. And so when you're looking at your homework, you're going to see notations with arrows. So if you have the 3p identical energy subshells, they'll be represented with 3 boxes. And so if you need to put electrons in there, you'll put in one at a time before you put in a second one. And they're going to have at most 2, and they're going to be shown with opposite spins. Nobody's going to ask you for this on a test, but these you will need for your mastering chemistry homework. Please follow the examples carefully. You'll probably be able to figure them out, and if you need help, do ask. So you'll need this for those assignments, the homework. And then you'll use these rules to figure out the electron configurations for the first 20 elements. Otherwise, you memorize them, or you use the S and the P blocks of the periodic table, which I find to be the most logical. So, following along, hydrogen has 1s1. You can represent it 2 ways, either as the name like this, 1s1, or you kind of just draw a line for the orbital and put an arrow in it. Each element has 1 more electron than the previous, so the next element becomes helium, and it's going to have a second arrow to pair up with the first arrow, and that gives you the second, the 1s2 notation with 2 electrons in it. So 2 electrons, 2 arrows. After helium, of course, then will come lithium with 3 electrons, and so 1s2, 2s1. Whoops, sorry, I keep forgetting to change my pen tool. 1s2, 2s1 means that you have one subshell s2 filled, and the second one only has 1. Going on from the lithium, you have beryllium. 1 more electron, so you fill the 2s2 subshell. After beryllium, boron is going to now go into the 2p subshell. The 2p subshell only gets 1 electron there, and so 1s2, 2s2, 2p1. It's in the first column of the p block. Carbon then will have 1 more electron than that, and so instead of just 1 in one suborbital, you'll have 2 separate electrons in 2 orbitals, but for our purposes, 2p2 will make a sufficient description. Nitrogen, as we mentioned today, has electrons in 3 types of orbitals. 3 types of orbitals, namely the 1s2, the 2s2, and 2p3. But technically there's 3 different 2p3 orbitals used to accommodate those 3 electrons. 2p3 is the way we will write them. Following that, of course, becomes oxygen. 1 more electron, and this time we will have a pair of electrons in one of those orbitals. But again, 2p4 fully describes it as far as we're concerned for anything you'll be tested on. 1 more electron gives you the symbol for fluorine, and that means it's going to have a total of 5 in the p orbitals, 2, 2, and 1. And the total valence electrons, again, remember, is the 2s2 and the 2p5. Then neon will be the one that has the 2p subshell completely filled with all 6 present, its valence electrons are the 2s2, 2p6. So, thinking about this and going on to how they correspond to the periodic table, the periodic table has periodic properties that have everything to do with electron configurations. The energy diagram in figure 2.6 refers to that. If you recall and think about dividing the periodic table into blocks, it tells you how the shells and subshells are filled. The name of the block indicates which subshell is filled last for these elements. Please do your best to learn this because it will make understanding the electrons' configurations much more simply. So you think within each energy level we have subshells with names of S, P, D, and F with different capacities of electrons, which we've already seen, and you'll have names that describe the shell and the type for every subshell. So there's going to be things like 1s and 3p, and sorry, my tool's in the way. Let me see if I can move this. Can I move the tool? There we go. And 4d is another electron subshell. And these will each describe shell and subshell locations for those electrons. So when you see this configuration for magnesium, it shows the first shell has 2 electrons, the second shell has 8 total in 2 different subshells, the third shell contains only 2. That's as far as it gets for magnesium, and it's 12 electrons. Total number is 2, 2, 6, and 2 makes 12. So when you have the s block, groups 1 and 2a, the s orbitals are the last electrons orbitals filled. For the p block, the last orbitals filled are going to be in p orbitals, and those are groups 3a through 8a. The d block is the transition metal elements, the f block are the intertransition metal elements, but we won't worry about them in much detail, just realize where they are, what the correlation is to electrons. The easy way to remember the order of the filling is to use the block system. You go across the rows in order of increasing atomic numbers, just follow across the numbers, the atomic numbers. The length of each period is determined by the filling of subshells within the shells. So these patterns are your ally as you are learning how to understand electron configurations. Make sure you cement them in your mind, draw them on your note card, doodle them onto the periodic table on your test when you get there if that's what helps you. And so hold on to these thoughts as you prepare and study.